All right, so now, what if we wanted to have an anti-Markovnikov addition? We wanted the halogen, the bromine, for example, to go on the opposite carbon, the other carbon, the non-Markovnikov carbon, or the anti-Markovnikov product carbon. So, for example, let's say we had our unsymmetrical double bond. And we want it to make the anti-Markovnikov product. That's what we want. This is the anti-Markovnikov product. The anti-Markovnikov product. To do that, you put peroxide down here. You add peroxide to the bottom. If it was just HBr, the Br would go here. But the addition of peroxide puts the Br on this carbon over here. Let's take a look at how that works. So first things first is you get what's called free radical initiation. In this reaction, the first thing to react is the peroxide. And they will do a homolytic cleavage to give you the oxygen radicals, oxygen-free radicals. The oxygen-free radical will now react with HBr. To give you bromine radical. Bromine-free radical, I should say. There you go. So now the bromine-free radical is now free to go and react with an alkene. And that will be under the propagation steps. Now the bromine-free radical is free to react with an alkene, and this will be what we call a propagation step. Okay, so now another molecule of HBr will get attacked by the carbon-free radical, giving you the product. Oops, we're out of space here. Giving you the product. Now, that's the mechanism, and that's showing you the anti-Markovnikov addition. Now, I want to go back and I want to explore this addition here. I want to prove to you that the anti-Markovnikov addition should work, because the bromide should, so the addition of the bromide here will give me the most stable radical intermediate, but I want to prove it to you. I don't want you just to believe me. So let's take the opposite approach. So here I had the bromide attacking the least substituted carbon. Now I'm going to have the bromide attacking the most substituted carbon. Now I want you to compare, if you would, this intermediate right here and compare it with this one over here. In fact, let me redraw this intermediate so we can have a very clear look at it. So this intermediate here is the one that's up here. So now, this addition is better than this one. Why? This is a tertiary free radical. This is a primary free radical. Tertiary free radicals are much more stable than primary. Therefore, the primary one will not form. The tertiary one will form and dictate the outcome of the reaction. All right? Remember, it's always the intermediates that dictate the outcome of the reaction. Whichever intermediate can form faster will have the product in the greater yield. It may be the only product as well, so keep that in mind. So let's do an example of anti-Markovnikov addition to an alkene. And let's do the addition to both. So that will react with a little bit of HBr and some peroxides. And that will give us, and let me just draw the product that doesn't form. The Markovnikov product does not form. Not formed. Okay. First step. Homolytic cleavage of the peroxide. And then HBr gets attacked, extracts the hydrogen off of the bromine, and you get the Br radical. This is the initiation step. Get everything rolling. Get that bromine radical generated. So now, let's draw two distinct reaction pathways here. Only one of them is going to work. One of them will give us a more stable intermediate. So this one, the bromine, will attack from the bottom to give us this particular radical. Now if we attack from the other side, attack the pi bond from the other way, you'll get the other intermediate radical. And that'll put the radical here. So this is secondary. This is tertiary. Tertiary wins. Tertiary is more stable, so tertiary is going to be the one that forms in preference. Now we have the more HBr comes in. And if you want to, you can just cross that one out because it's not going to do anything because it doesn't form. And you attack that and you propagate the reaction. You keep it going in a chain reaction. And you generate the product. And there you go. That's how you would do the mechanism for that particular example.